So yesterday we talked about continuous growth applications or doubling when things grow continuously or knowing their double rate. Uh, Now we're going to talk about going the other way. We're going to talk about decay. So when things get 50% of what they had before, it's called the half-life. So 75% of what they had before would be a three-quarter life. If there's only 25% remaining, that's called quarter life. Our basic focus will be the half-life problems, but we'll extend this to other types. We'll do what we did yesterday and show how we can go from a half-life with a base of 2. I know you're thinking 1/2, but we'll show how to get that 2 into a 1/2, how they relate with exponents. We'll take that and turn it to a base of e, so we can use our continuous decay formula. And then we'll talk about how to use the half-life to determine your rate and how to make growth models just like we did yesterday. So everything's decaying. And then we'll get into a very special case of an exponential decay problem called Newton's law of cooling. And we can show how that can be used to figure out temperatures of items, and the real application where a lot of people like to use or used in the past is how to find out time of death problems, which we will throw on the test as a bonus problem. So let's start off like we did yesterday, except for I'm going to give you an element that decays naturally rather than the bacteria that's growing continuously. And we're going to give you its half-life, okay? So every 8 days, the amount of iodine, the 135 is just an isotope. Don't worry about that. That's not needed in calculation. It's part of the name. So your iodine gets cut in half every 8 days, and you start off with 128 grams. So in 8 days, that amount is going to be half of what we had before. So half of 128 is 64. Okay. So we're going to finish this table here to show that we're going to cut it in half 4 different times. So in 16 days, 8 days from now, or 8 days from the first time it got cut in half, it gets cut in half again. And in 8 more days, it's cut in half again. And 8 more days later, it gets cut in half once again. So we have our table going on here. And now we're going to use this table to figure out a model that shows what's happening here. Okay. Now, there's 2 different ways we can do this. We can do this with a base of 2 or a base of 1/2. I'm going to go ahead and do with a base of 2. And just remember that 2 to the negative 1 equals 1/2. Try that down here. Okay, so we started off with 128. And then we had 128, and we divided by 2 or times by 2 to the negative 1. So right here, I'm going to split times 2 to the 0 to try to keep a pattern going. So 128, and we divide it by 2. So 2 to a negative power, and we did it twice. Cut in half again. Then we divided it by 2 3 times. So negative 3 would be our power. And if we divided by 2 4 times, our power would be negative 4. So what we want to do is what we did yesterday in our notes. And we want the powers all to have something with these numbers right here, so we can eventually turn that 0, 8, 16, 24, 32, wherever we see that number, into a t. Okay. So I got to think about, what do I have to do to 0, 8, 16, 24, and 32, turn into the numbers 0, 1, 2, 3, and 4. Well, these were going up by 8s, so how about we divide by 8? So 128, and let me go ahead and just put negative 0. I know it's kind of weird, but that'll help us out. Negative 0 divided by 8. Sorry, that's times 2 to that power. So 128 times 2 to the negative 8 divided by 8. That gives us our negative 1. So 128 times 2 to the negative 16 divided by 8. So 128 divided by 2 to the negative 24 divided by 8. and the 128 times 2 to the negative 32 divided by 8. And that would give us the powers we see. So the things that I see changing from each part of the table, just these numbers right here and these numbers that are different are the exact values of t that we have in our table. When I write my equation for this, I'm going to write exactly what I have for each number, except for use t instead of those red numbers. So we have 128 times 2 to the negative t divided by 8. Now, some people would have just same formula looks a little bit different. Some people might have 128 times 1/2 to the t over 8. They might take the negative part of the power and flip the base. But I'm just going to leave it what we had before, because some things that I remember from what we talked about depreciation decay problems in the first half of this unit was they had a negative rate or a negative power. So why don't I keep it the same? So that way I don't have to keep changing my base. So we're cutting this in half. That's why it's 2 to a negative power. All right. So the next one says how much iodine was left after 1 day. Now these were in days for this. So when I do this one, this one's probably not going to be a nice number. What the M is standing for in this problem is the mass. So that's when they're saying how much the amount. They're looking for the mass. So the mass of one that's left after 1 day would be 128 times 2 to the negative 1/8. So I'm just going to go grab my calculator, and I'm going to go ahead and put in my 128, that's my P, times 2 to the negative, that's my base is 1/2, that's why there's a negative there, and then 1 day, and it cuts in half every 8 days. So I'm coming up with 117, and since this is not a living item, we're going to go to 3 decimal places. 300 or 117.3765. You can round or truncate, it doesn't matter. And the label they were using for the amount for the mass were grams. So G. Now we talked a little bit about reasonableness yesterday. Let's see if there's a reasonable answer. Well, 1 is between 0 and 8, and 117 is between 128 and 64. So that seems like a reasonable answer to me. All right, part C is done. Let's move on to part D. So they want to know how many days will it take for only 10% of the iodine to be remaining. All right, so 10% remaining would be 128 times 10% remaining. Now there's something you got to pay attention in these type of problems. There's 2 different things we can talk about. We can talk about the percent remaining, okay, or the percent that has decayed. In these problems, the M of T is what remains, not how much has disappeared, gone away, but what's still there. So make sure you read the problem correctly. If I had said 10% had decayed, I'd be using a 0.9 for 90% remaining. So pay attention to the English in the problems. So that's how much we have left. We got 128 times 2 to the negative, and we do not know the time. By the way, this is what, 12.8? So if I'm looking at a reasonableness for my answer, 12.8 is between 8 and 16. That means that it should be between 24 and 32 days. So I should get something more than 24 days or less than 32 days, or else I've made an error. Okay? So I'm going to divide by the 128, and that's where we're going to get the 0.1. Huh, just a ratio. Gives me that 10% right back. There might be something to that. Okay, so now I'm going to go and continue to solve. You could take the natural log of both sides and then take the power out in front, or you could take the easy way and do log base 2 of the number, which was that ratio of what remains, equals negative t divided by 8. So I'm going to times by 8, divide by -1, or times by -8. I'm going to go ahead and use the change of base formula. So those of you who don't have the special button in your calculator can calculate it with us. So I'm going to change the log base 2 of 1/10 to the natural log of 1/10 over the natural log of 2. And there's my t. So grabbing my calculator, I have -8, the natural log of 1/10, and divide by the natural log of 2. So we come up with 26.575 days, which is what we said needed to happen between 24 and 32 days, according to our table. Now, if you wanted to use this formula right here, it would work out very similar for part D, except for what you would have had is you would have the natural log of 1/10 divided by the natural log of 1/2. And then that would have been times by 8. So that negative would have been popped up as a power for your here, this problem. So sometimes you can see that half, hey, this was a half-life problem. So that's another way you could use it. You could use this if you really wanted to. You won't see the negative, you'll see a half. Either way works. Okay? So here's the way the book writes it with a base of 2. That's how I did the problem initially. Or it is completely acceptable if you rather think of it, okay, it's getting cut in half, so my base is 1/2, you can do that, where you do t over h. So that really is a half. Don't care. Your choice. If you're going to use 2 for the half, that's fine. H is the time it takes to reach its half-life. So that was the 8 days in the previous problem. So it's the same thing we saw for double time as half-life, except for using a negative exponent, or you change your base from 2 to 1/2. Do one of the two things, not both. If you do both, you're talking about double time, not half-life. All right, so we saw how we could use ratios before, and we can do the same thing. It doesn't matter if it goes from double to 1/2. The only thing that we realize is when we calculate this with 1/2 is that we're going to get a negative rate, which makes sense. It's decaying. So you put your ratio right here. So in that last problem, we had 1/10. If we knew our growth rate, how much time it took to get 1/10, we could have worked out pretty quickly. Okay, so you put your ratio inside the logarithm. So quarter time, you're going to put a quarter. 10% left, you're going to put 0.1. So you can use your magic little triangle we talked about before. So if you want to find the rate, that equals the log of the ratio over time, right? If you want to find time, take the natural log of the ratio over the rate. If you just want to remember that the natural log of the ratio is the rate times time, then you can use a little algebra to solve for whichever piece you need to look at. So we can figure out our rates using the half-life, then we can actually get this pretty quickly. Now, I don't like them saying this right here. It really should have a negative here for the number when we actually look at it. So they put, to take care of that, they put the negative here. To make things a little bit more like what we've already done, I would just say your rate is the natural log of 1/2 over the half-life. And your formula, how about we not learn another formula? So how about we instead of using m sub 0, we use the initial amount, the amount prior to the time. And instead of the function notation, you can use it if you'd like. We call it a. And then we just have e to the RT. Because when you calculate this r is going to be less than 0 anyways when you use a half here. So you don't have to worry about making a negative. This is the way I would study it, so you don't have a new formula. You're using the exact same formula you did in the first day of section 4.6, the exact same formula you saw when we did problems in 4.2. It's the same formula. So that would also help us keep one formula for this. It's the natural log of the ratio divided by the time it takes the ratio to get your rate. So I actually think of this. Rate times that time it takes to the ratio gives us natural log of that ratio, your A divided by P. All right, let's redo the first example. But this time we're going to use the continuous growth decay model that we have, the natural, the one with a base of E. So we have the same amount of iodine, 8, and it gets cut in half in 8 days. Okay, so this is your initial amount P, and this is the ratio, or this is the time for it to get cut in half. So your ratio, your A over P equals a half when your time equals 8. They're connected here. Okay. All right, so let's go to part A. Find your relative rate of decay if you know the half-life is 8 days. So you just take the half-life, natural log of 1/2, and you divide it by the number of days to get there. Oops. So we go ahead and calculate this, and we'll store it in our calculator. So the natural log of 1/2 divided by 8, and I'm just going to store this in my calculator for later use. If it's not a negative, I've screwed up. There we go. So this is approximately negative 0.08664, which correlates to a growth rate of 8, or decay rate of 8.664%. We just say rate of decay. All right, I'm going to store that for later. Part B, use the relative rate to find a formula. So I'm just going to use my PERT formula. So A equals the initial amount that we had, which was still 128 grams. E, our rate of decay, divided by 8 times T. So now we have our formula. By the way, it's okay to write your rate for an answer on a test as a natural log. Okay, clean that up. All right, part C. How much is left after 1 day? Should be the same answer we had before. So we're just going to put 1 in for our time, since our time is a measurement of days. And then we're just going to plug it into our calculator. So 128 E to the natural log of 1/2, or 0.5, divided by the 8 days it takes to get there, and we're going to do just 1 day. And we get the same 117.376 grams that we did the first time we did this problem using the other formula. All right, we got one more part to this problem. It says, how many days will it take for only 10% of the iodine to remain? So we could just do what we did before and put the 10% of 128 is 128 e to the natural log of 1/2. I'm just going to use a decimal this time, over 8. And I could divide by the 128. Then I can convert this to a log. So it's log base E of the number 0.1 equals my, and the question is how long. So sorry, I need a T. The exponent, which is natural log of a half over 8 times T. So times by 8, divide by natural log of a half, or I could just say divide by that rate I had and gets my answer. Here's the thing. You could have come straight here. If you knew your ratio was 1/10, you could have just put that in here, right off the bat. They told us that the ratio was 1/10, 10% remaining. And then you could divide it by your rate, divide by a fraction, multiply the reciprocal. So I could have come here immediately without any work, and I would have been just fine. And once again, we can throw this in our calculator. It should be the same amount that we got the first time we did this problem, which was 26.575 days. Okay, so if you think you have the gist of this, you can start your homework. If you want to see a couple of examples like the ones in your homework, stay with me and we'll go through some problems here. Okay, so the first problem is trying to get us to use the base of 2 with the negative power here. Okay, so they want us to find a function in this format, then they want to find a function with the e. Okay, so we're starting off with, let's see, 10 grams. That is our m sub 0 in this problem, or in PERT talk, that's p. Okay, and the half-life is 30 years. Okay, so that's the h for part A. So for part A, the mass as a function of time is going to be 10 times 2 to the negative t over 30. The other way we could rewrite this or make this problem happen is we could find our rate. So our rate of decay would be the natural log of 1/2. If you prefer, you can do negative natural log of 2. Okay, all over the amount of time it takes to get that half-life. I can write down my function of time is the initial amount, 10, e to the natural log of 0.5 over 30 times t. If you want to do natural log of 2, you would put a negative there. Okay? So we have the function written 2 different ways. Okay? So the next thing we're going to do is we're going to write down how much of the sample remain after 80 years. So our time is now t, and what they're looking for is how much remains. So for part C, you could use either one of these. It doesn't matter. So I'm going to write down the mass of 80 years is 10 times e to the natural log 0.5 over 30 times 80. So this becomes 10 second natural log of natural log of 0.5 divided by 30 times 80, which tells us after 80 years, there's only 1.5 7, I'll round this time, round or truncate, grams. Okay, and they said years. Okay, so let's see if that seems reasonable. So in 30 years, it gets cut in half. So in 30 years, there'll be 5 left. 30 more years, or 60 years total, there'll only be 2.5. In 30 more years after that, there'd only be half of 2.5, which is about 1.125. So we're looking for something between 1.125 and 2.5, which is what we came up with. Okay, the last part of this problem, part D, says how many years will only 2 grams of the sample be left? So I'm going to go use the same concept. I'm going to go use my PERT formula. And then I would divide by 10, then I would change it to a natural log and then divide by the ratio, or the rate. So you can work it out. So 2 divided by 10 is 0.2. Or you could think, hey, there's only 20% remaining. So if you really wanted to, you could do natural log of the ratio that's remaining, natural log of 20%, and then divide by your rate. So when you divide by the rate, you can multiply by the reciprocal, and now it's just plug it in my calculator. So you can show the work and get here, or you can go straight here right away if you really understand that ratio. So natural log 0.2 times 30 divided by the natural log of a half. And we come up with the time is 69.6578 years, which makes sense. If there's 2 grams left, that means that happens in less time when there was 1.75, and it took 80 years to get there. So it should be smaller than 80 years. And we already talked about if you cut it in half twice, you go down to 2.5 years would be, or 2.5 grams would be at 60 years. So this seems reasonable. All right. So this next problem, when you first read it, you feel like there's a lot of missing information. There's no way you can answer it. But here's the thing about exponential growth. We talk about if we know the rate at things grow at or decay at, we don't need the initial amount to predict the percent that's going to be left. It won't matter. So we're asked to estimate how long ago this mummy was buried if it contains 59% of the carbon-14 it normally had. So what we do know about carbon-14 is it takes about 5,730 years to reach its half-life. So that'd be 50%. So I can tell you right off the bat that if there's 59% remaining, it has not reached its half-lifetime. So the answer has to be smaller than 5,730. Again, having reasonableness is a huge important thing with these problems. It helps you understand if you're doing them right or not. So let's get some information we do know. I can find out the rate immediately. The natural log of a half. I'm given a ratio of half. I'm given the time it takes to reach that. So if I would take the natural log of the ratio divided by the time it takes there to get there, I have my rate. And if you want to throw that in your calculator to see what it is, great. So the natural log of a half divided by 5,730 should be a negative since this is decaying. Now, that capital E at the end of the problem really tells me that that scientific notation, going to add in 4 zeros. So 0 point, put a decimal after the first one, 2, 3, 4, 1, 2, 0, 9. Okay, I'm going to go ahead and store this number in A so I can use it later on. If you want this as a percentage, you would times by 100. When we write percentages, we don't write the positive or negative. So it has a decay rate of way less than 1%. So if somebody's asking the rate of decay as percentage, that's how you would write it. I'm good with any of these three representations of the rate of decay. Normally on a quiz and a test, this is part A of the problem. What's the rate of decay? Okay. All right, so let me put that number back up there for our rate of decay just so we can see it. Now I'm going to go answer the real question. How long ago was this mummy buried? So what they're looking for is they're looking for the time. But they've given me that ratio, the amount after the time has gone by divided by the principal. They've given that was 59% or 0.59. That's my ratio. So I can solve this super fast. I just take to find that time. Take the natural log of the ratio. And I divide it by the rate, which I just found in the first part of this problem. So I alluded to doing this really quickly on the last couple of problems where you didn't have to show all the work because you don't have to. Now, if I want to clean it up, make it easier to type in the calculator, I might just multiply by the reciprocal of this denominator. So 5,730 natural log of 0.59 over the natural log of 0.5 or a half will give me the amount I need. In my calculator, I'm just going to do natural log of the ratio I want divided by the rate, which I stored in as A. So we said it was going to be less time than the 5,730 years, and we're coming up with 4,361.751 years. And that's all there is to this problem. So this would be very much like something you might have to do on a quiz and or test, but definitely I know for sure on the quiz, and there's problems like this in your homework. Okay. All right, so we are done with the normal part of the half-life and the decay problem. We're going to go into just extension right now into Newton's law of cooling. So we're going to talk about how an object cools. So if an object is left in a room, it's going to eventually approach that room temperature. So if your room is always set at 70 degrees and you take a hot cup of coffee in one side of the room and lay it down, and you put it on the other side, ice cold of water and lay it down, after enough time, when you go take the temperatures, it's going to be the same as that 70-degree room. So that's what we're saying. So it's going to approach 70 degrees. Now the coffee, mathematically speaking, will always be a little bit more than 70 degrees. And the water will always be a little bit less. So what happens here is you got hot coffee and it cools down quickly, then it slows down and approaches the room temperature. Or ice cold water warms up and approaches room temperature. Now you might be wondering, why is it called cooling if the water is warming up? Well, it's called cooling because it's like decay or depreciation problems. The rate is negative. It has a horizontal flip in the graph. It means that when we graph it, the graph of this, it's going to approach the horizontal asymptote as the time goes to infinity, or on the right side of the graph. So the distance between here is getting smaller. The distance between the item and the room is getting smaller and smaller and smaller. So that feels like K means, which kind of goes more with cooling than the word heating. That's why it's minus. All right, so in Newton's law of cooling, we're really just going to see Hertz, but the T is not the initial amount, plus a number. So it has this format of a number plus Hertz. We will give you this formula on the test somewhere. We use it. We do not memorize this algebra. Okay. Well, this really right here, this TS really is the horizontal asymptote at room temperature. Called surrounding temperature. So the S is surrounding temperature. So what this D sub 0 is, it is the distance between the room and the item at the very beginning. So if you would take your item and then subtract your surrounding temperature, you get this D sub 0. So in a problem like this one, your initial temperature of the coffee minus your surrounding temperature would be the base or the number in front of that base, in front of that E. And you'd have that surrounding room. 70 plus whatever the coffee is minus this. When you do this, that will give you a positive number, which means no vertical flip. You only have only the horizontal flip. Remember, the growth normally looks like this. So with the cooling, the flip like this. If we're getting a hot item cooling down, it'll have a plus sign here. In this situation, when you do your 70 plus your minus room, okay? So whenever you do this right here, I can back out a little -1 here. It'll look like a minus down here. So if the item is warming up, you're going to see a minus in here. As for reasonableness, you should get the same thing every single time. Order matters. You're going to take the temperature minus the surrounding temperature. And that's always how you're going to get what we think of as P from our PERT. So again, it's like PERT plus a number. Okay, so we're just changing our horizontal axis. K is the rate of cooling. It's cooling. The K has to be a negative. We're saying right here. Cooling tells us to be negative. The other two things are variables. A little t is your time, capital T is your temperature. It's just any multiplication that comes to no t. So if you'd rather write temperature equals surrounding temperature, it's the difference of the surrounding temperature room temperature. E to your rate times your time. That's fine. Okay. So the horizontal axis open Newton's law of cooling. What is the sign of it when it's cooling? So it's hot things, so the initial temperature is bigger than the surrounding temperature. So big number minus small number is greater than 0. So it's positive. Okay? The picture is kind of explaining my why. So what if it's warming up? So here's your initial temperature. Here is your surrounding temperature. So T sub 0 would be the initial minus surrounding. So if it's below the initial, you subtract it, you are going to get a negative. Why is it called cooling even if it's warming up? Because your rate is less than 0. You're going to always see, if you would put it as a plus, you'll always see a negative in the x. All right. So this is our typical problem we put on the text and on the quiz. We will give you the formula to start with, and you just have to figure out the little pieces. You got to calculate T zero. You got to calculate K. We're going to be given the surrounding. Okay. And then you're going to answer a follow-up question after you get the formula. Okay. And sometimes part A is n value K. And then you can write the equation. So our formula, temperature is the surrounding temperature, the temperature of the initial surrounding. E to our rate, K to K, B. The book will put a little negative up there, just remind you that it's negative. It'll calculate fine. Okay. All right. So some of the things you have to make sure is you have to take the time to read. It's really easy for somebody surrounding temperature and initial. If you do that, you change it from a cooling to a warming problem or warming to a cooling problem. How to make sure your answer makes sense. We're taking a cold turkey and putting it in the oven. So the initial temperature is 37 degrees. So at 0 hours, the temperature is 37 degrees. The 325 is your surrounding temperature. If you leave the turkey in the oven forever, eventually it will cool to 325 degrees. Just 25, unless 3 is higher than it's you got to start. Okay, so our surrounding temperature is 25. So start off. I have 325 of the oven. it is warming up. So we're actually going to see a negative right here. So our difference would be temperature at first minus the number you put over here. So we're just going to go calculate that. 37 minus 325. We're getting negative 288. That's why we knew it was going to be a minus, which makes sense. It's going to be E to K, P. So the next thing we need to find is K, and then we'll have our function. So this is when we're going to go take a look for a pair of specific time with a specific temperature. So after 2 hours, somebody took the temperature of the cookie and found out it was 110 degrees. So we're going to put 110 in our time, and the 2, sorry, in our temperature, and the 2 in our time. So let's go and subtract 25. Then we're going to divide by the number in front. Then we're going to go convert it to a logarithm to get this. So you don't have to little by little step by little step if you want that fine. We're going to divide by 2 or get our K. I'm going to go ahead and store this number. It's kind of ugly looking, and I will probably write down the decimal value in my formula. I will use the stored value in my calculations. So we got a half times the natural log of the quantity 110 minus 325 all over negative 288. If you get an error, that means you probably switched something off or put a sign error early on, but more likely you switched for you probably switched your initial temperature and your timing. You should be getting a negative if you've done it correctly. So our rate of cooling is negative 0.14616, whatever. I'm going to store it so I remember it and write it down again. All right. So on the test, a lot of times we'll say, C, find K, be done, dispatch the right function. So the temperature as a function of time, we lost the function is 325 minus 288 e to the negative 0.146 and time. The next question says, how long will it take the internal for the cookie to reach 165? The reason why they want to do that is so we know the temperature is 165, and we're looking for T. So I'm going to isolate. So I'm going to subtract the 325 first. And then I'm going to divide here that time. Then I'm going to have to get rid of my exponential. How do you get rid of a base? How do you get rid of this? You convert it to a logarithm, so log AT. Then I'm going to get rid of this multiplication by dividing by that P value that's if you need to, again, show all the little steps at a time, go right ahead. So I'm going to take natural log my fraction, going out of these calculator helps. 165 minus 1.5 all over negative 288. And then I got to divide that by my K, stored in as K in the calculator. And I'm getting approximately, for my time, that put it in units of hours. So 4.0214 hours. Be careful. Sometimes textbooks or questions might ask a question like, how many more hours do you have to wait? Well, we already found we waited 2 hours to start with. We get 110, 2.0214 more hours. They just asked how long, total time. So this is it for what we expect on the test. I want to stay with me still. You can do this problem and follow along. The a bonus problem. We will put this in one of the work this problem out. You'll see some things like this in the homework. They normally give you the K, make it a little bit easier. Okay. So before they had some other things and stories of science, one way to figure out how long I had time is when you kept the room with a conference is that delivered. And they would assume they didn't have a fever, that's part of it, or if they thought they died of a certain illness, then they would assume what the temperature would be, what's the common for that, and then they would just give an estimate. So there will be some error in this, but we want to make sure we get a reasonable time. Okay? So in these type of problems, what I'm going to do is the time of discovery, the time equals zero. So at time of discovery, body temperature was 84.1 degrees. So that gives me an order pair of 0, 84.1 degrees. Now, we know that a human body, this is what we're looking at, 98.6 degrees, human body. We know that that's the normal. So this body must be cooling down. So that means to get 98.6 degrees is what we're looking for the time of death. My T better be a negative value, so I'm going to do it the way I'm setting it up. Wrong. So the 70 degrees right here is turning. Now the 11 a.m., I'll come back to the end because past the time of death, we'll talk about what time on the clock. Okay, so let's go set this up. My T sub S is 70. My D sub 0 is initial minus rounding. So 14.1. So my formula will be surrounding. We got a positive e to the k. At this point in time, it's very much like the tricky problem. I need another word here. So 1 hour later, it drops 79 degrees. With 79 in front. And I'm going to put 1 in for my little t. And the reason why I like 1 hour is it makes the calculation a little bit easier. And we're going to solve for k. So order of operations. So at 79, we're going to subtract 70. Then we're going to divide by 14.1. Then we're going to undo the exponential function. We're going to use a logarithm. And there's nothing times k because it's just 1. We could divide by 1, but we don't have to. We got our k. Let me go ahead and put this method test. So we had the natural log of 70. Try that again. Of 79 minus room temperature over the difference. I'm going to go ahead and store that A. So there's my K value. All right, let me rewrite my formula. So now we have T equals, it's still 70 plus 14.1 E to the negative 0.448 T. Now I'm going to look for that little t when the big T is 98.6 degrees. All right, so I'm going to subtract my 70, divide by my 14.1, take the natural log, get rid of the e, and then divide by my value of k. Again, do not use 448 in your calculator. Use the stored value so you can get it to the nearest minute. So let's go calculate this. And if it's negative, I'm happy. Because if it's positive, it means it's right after they were discovered. All right. So we have natural log the temperature 98.6 minus 70 all over the divided by our rate of cooling. And I'm coming up with approximately negative 1.575 hours. Now, if this is the bonus problem on the test, I'll be giving you 7 out of the 10 bonus points. The reason why you don't get them all is because they said, what is the final temperature nearest? They want a time on the clock. So what I'm going to do is I'm going to turn this by 60. Okay. So that's 95. Before 11 a.m. Now I'm probably giving you like 8 or 9 of the bonus points. To get the last one, I'm going to go figure this out. This is 1 hour and 35 minutes before 11 a.m. 1 hour gets us to 10 a.m. 35 minutes before that gets us to 9:25 a.m. And there is the time of death. The quarter law, probably giving you an error, like a half an hour or so. Like, hey, this is where we're going to see this motivation. All right, so you should be able to finish day 2 of the bookwork. And then from the worksheet, that's going to be tomorrow. Number 4 comes from the first grade notes. 6, 2 notes. I think that's how this section. That's a worksheet. You know what to say down here. Let's do the work. Okay. That's page